Hello everyone. Today we're going to go over various derivative interpretations, one including rate of change problems, and the second being slope of the tangent line problems. Um, and we talked about before how different rates share the same limit, like the instantaneous rate of change shares the same limit as the limit for finding the derivative. And basically, we're going to be using this knowledge that we've attained over the past few videos in order to solve a few word problems that include derivatives and finding the rate of change and various other problems that are going to have a very similar formatting to what you're most likely going to be seeing over the course of taking Calculus 1. All right, so the first type of problem that we're probably going to be going over is rate of change. So basically, if f of x if f of x represents a quantity at any x, then the derivative, let's say the d over d of x. This means the same thing as the derivative dy over dx, d over dx. Then the derivative, or we'll say, well, I mean, for what we're doing, say the derivative f prime of a represents the instantaneous rate of change at x equals a. All right, so for our first interpretation of a derivative, which is the rate of change, basically it states if f of x represents a quantity at any x, then the derivative f prime of a represents the instantaneous rate of change at x equals a. So basically this means that for these kinds of problems, we're going to be given a point, and we're basically going to be told essentially to find the rate of change for the given function at the given point, which is going to be a. And basically, we're going to plug in that value of a back into the derivative that we have found for f of x. So let's go ahead and take a look at what that would look like in word form, in the form of an example. All right, for our first example, we'll say um, suppose the amount of I mean I could have written down water, but I just chose to do H2O. 15 minutes is given by v of t, which is equal to to t squared minus 16t plus 35. We're going to determine the following. Well, actually, we'll just start with A. Say A is the volume increasing or decreasing at t equals 1 minute. We're gonna do a few, I guess. Whoops. We're gonna do a few, I guess, problems like this, like like A. We're gonna look at different t values, but so we're asked right here. Wait, let me line this up. We're told, suppose the amount of water in a holding tank at t minutes is given by V of t is equal to 2t squared minus 16t plus 35. And then we're asked, is the volume increasing or decreasing at t equals 1 minute? Now this might seem a bit confusing, and it definitely is because, well, this is a word problem that we've been given right now. But for the examples in this video, we're going to be looking at problems that are worded similar to this, and they all somewhat have a very similar, like, I guess, line of progression. So the first thing that we're going to want to find is our derivative function. So we have v of t. We want to find v prime of t. But more importantly, we want to find v prime of a, or in this case, 1. So, wait, I don't know why it's orange. V prime of t is just going to be equal to the derivative of 2t squared minus 16t plus 35. And in order to find the derivative for this function, what we're going to do is multiply the exponent by the coefficient. And that'll give us 4t. But basically we subtract 2 by 1 because we're multiplying it out. So now it is 4t. And for this, the t goes away, so it's just minus 16. And there's no constant that is included in the derived version of this function. So now we have v prime of t. Now we're going to do v prime of 1, which is just going to be equal to negative 12. So it's asking, is the volume increasing or decreasing at t equals 1 minute? Remember that this is the given rate of change, right? If it's a rate of change, if it's negative, that means it's going downwards. Or rather, it's decreasing. So the rate of change is decreasing because it's a negative value, so we would say that it is decreasing at t equals 1 minute. Let's take another, not another look, but let's do another one. Another small little problem. This time we'll say t equals 5. And basically it's just going to be the same exact thing. V prime of t, as we said before, is going to be equal to 4t minus 16. And at v prime of 5, it's just going to be equal to 4, I believe. Yeah, 4. So because it's a positive, the volume at t equals 5 is going to be increasing. So yeah, it's not very, it's just finding the derivative to the function that we're given and then plugging in certain values for the rate of change. Now, based on the two answers that we found at t equals 1 and t equals 5, is the volume um, I guess in water, or not in water, but in tank. And is is the volume in the tank changing faster at? Okay, yeah, that makes sense. Sorry, I had a grammar issue. So is the volume in the tank, or the volume of the water in the tank, changing faster at t equals 1 or t equals 5 minutes? In order to solve this problem, looking back at our last answers, we were given, I believe, -12 for t equals 1. And for t equals 5, we were given a positive value. In order to find the answer to a problem like C, we're just going to have to compare v prime of 1 and v prime of 5. And based on which one is bigger, let's say for v prime of 1, it was, I guess, -12. And for our v prime of 5, it was 4. But the thing is, we're going to basically ignore any negative or positive value just due to the fact that we're trying to find which one is changing faster. So it doesn't matter which direction it's changing in, whether it's down or up, whether it's negative or positive. What does matter is the actual rate at which it is changing. So, so that's why we're barring it. And in this case, at t equals 1, that's when it is changing the fastest. So let's go over another example. Or actually, let's do one more thing. We'll ask. So I'll ask right now. We'll say for D, we'll say when is there no change? So since we're asking when is there no change in the function, we're just going to set v prime of t equal to 0 because that is the rate of change. V prime of t is the rate of change. If we equal it to 0, we'll be able to find where it's not changing. So it'll just be 4t minus 16 is equal to 0. 4 is equal to 16, or 4t is equal to 16. T is equal to 4. And that is when our function, or at least there will be no rate of change for v prime of t. So we would say t equals at 4 minutes, basically. Let's go ahead and go over the next topic, which is going over the slope of the tangent line and problems that have to do with that. So let's go over our general definition first. So we'll say for the slope of the tangent line, say the slope of the tangent line to f of x at x equals a, which is another given point that we will be given by the problem, is f prime of a. Tangent line given by the following formula, which is just going to be y is equal to f prime of a plus, or f of a, sorry, plus f prime of a x minus a. So whenever we're going to be asked about finding the slope of the tangent line, we're going to be given a point for one, at least for these problems we are, and basically we're going to have to find f prime of a, with a being our given point, in order to fulfill this equation down here. So we're going to have our f of a, f prime of a, and our x minus a right here. And once we find all of these values, then we would basically plug that back into our, I guess, equation right here in order to give our slope of the tangent line. So let's take a look at a example of how this would look like. So example 2, find slope of the tangent line, find saddle to r of x at x equals a. Or not x equals a, but I guess, well, I mean x equals a being 3, whatever. And we'll say r of x is equal to square root of f of x minus 8. So go ahead and try this. Really, this is just plugging in values to a equation. So it shouldn't be too hard, and using the terminology that not using the terminology, but using the same progression that we used for the past example, we can easily solve this problem. So give it a try and see how far you can get. All right, so finding the slope of the tangent line to r of x at x equals 3. All we're really just going to do is find r prime of x. And r prime of x in this case, I guess we could do it here. We could use the limit definition that we had set up last video, but instead, so just as a lesson, when there is a square root around an equation, this just means that it is 1/2 exponent. So it would pretty much look like 1 over 2 5x minus 8 negative 1/2. And also, x is multiplied by 5, so it'd just be 5 over 2. So that would basically give us 5 over 2 square root of 5x minus 8. And now we just need to plug it in for 3. So r prime of 3, or actually, we'll have this here, but we'll first say r of 3, because we need both r of 3, r prime of 3, x minus 3. Yeah. So we'll say r of 3 equal to, uh, I guess, square root of 7. And r prime of 3 is going to be equal to 5 over 2 square root 7. Just erase this for now, because we got what we need for our equation that we're going to plug in these values into. So our tangent line and as we said before, it's y is equal to x, f of a, which is just going to be r of 3, so square root of 7, plus, I might have said minus before, but it's actually plus f prime of a, which is 5 over 2 square root 7, times x minus a, which is 3. And that is going to be our final equation for our slope of the tangent line to the function r of x. All right, so that basically goes over both, I guess, interpretations, or two interpretations of the derivative. But there's also going to be another kind of problem that you guys might run into, and those are velocity problems. So I'll just say, in terms, or not in terms, but more so for velocity, we're going to say, actually, let's change up this color. Not red, just a red. If the position of an object is given as f of t, and we don't say f of x, I mean f of x, f of t. I mean, you could write it however you'd like, but we'll say given as f of t after t units time velocity of the object t equals a is given by f prime of t, or f prime of a. Sorry. So for velocity, if the position of an object is given as f of t after t units of time, the velocity of the object at t equals a is given by f prime of a. So this is basically the same, well, not the same as the last one, but two examples ago, not the slope of the tangent line, but the rate of change problems. We're basically going to be finding f prime, and then we're going to be plugging in the value that I guess a gives us. And based on that, we can tell certain things in regards to the object, the direction it's moving, right, left, or when it stops moving. So we'll go over a practice problem right now. All right, so suppose the position of the object after t hours is given to us by this function right here. G of t is equal to t divided by t plus 1. For our first question, we'll ask, is the object moving to the left or right at t equals 10 hours? Is the object moving to the left or right at t equals 10 hours? So this is pretty similar to the problem that we had before, asking whether or not the rate of change is increasing or decreasing. This is the same logic. If g prime of 10 is positive, that means it's moving to the right. If it's negative, then it's moving to the left. So let's take a look right now. Whoops. Don't want to move all that. Go. All right. So g prime of t is going to be equal to 1 over plus 1 squared, because a negative 1 goes to a negative 2, and a 1 goes to 0, because we have to do n minus 1. So g prime of t is equal to 1 over t plus 1 squared. And now we're going to try to find g prime of 10. T equals 10 hours. And that is going to be equal to 1 over 11. Or at least it should be 10. Oh, g prime. Whoops. Sorry. I was looking at my notes. I was like, what the hell? 1 over 121. 11 times 11, yeah, 120. And because of the fact that it is not a negative, it will be, I guess we could just say right, due to positive. So for our next question, the object ever stop moving? And this is a very similar question that we've asked before. And basically it's going to be the same exact thing, g prime of t equaling to 0. However, if you notice something about g prime of t, I'll write it down for you guys again. 1 over t plus 1 squared. We can't really find a 0 value for this. If we were to set this equal to 0, we wouldn't be able to really get this down due to the fact that this is a fraction and it has a numerator, right? So we can't possibly find a value where t is equal to 0. Or not t equals to 0, but this function equals 0 or is not moving at all. So for this, we will say no. The object never stops moving due to the fact that we cannot set this equal to 0 and find the 0 of t plus 1 squared. We can get this to be undefined, but we can't really get this fraction to end up equaling 0 due to the fact that the numerator is 1. So yeah, these are a few problems that go over the interpretations of derivative problems. Essentially, they're just word problems for derivatives. They all follow a very similar like train of thought when solving these problems. You'll try to find the derivative for the function given. You'll be given a point that you could plug into the derivative in order to determine whether or not it's moving left or right, if the object is moving is left or right, or if the rate of change is positive or negative. And you'll basically go on from there and be able to give your answer. And yeah, that's basically it for interpretations of derivatives. This isn't a very um, subject packed, I guess, subunit. It's just basically giving you the tool set to solve word problems in regards to derivatives. So yeah, I will see you for next video, and we'll be going over NeetCode 5.